Okay, gentlemen, welcome to Electricity Lab number 6, Resistance in Parallel Circuits. So we won't be doing this lab as a virtual online simulation via the FET simulator we've been using previously, just because the ohm meter setup doesn't work as efficiently as we would like, and not as efficiently as the Sigmatrons would work if we were to be conducting this lab in real life. But given the parameters of virtual learning and the pandemic situation we're in, we're going to make the best of it via one-note recording here. Okay, so pretend we've obtained a Sigmatron board and 4 100 ohm resistors. We know that ohm is the unit for resistance, and we want to use these resistors to test our theory of parallel circuits. Okay, so we're going to employ some Kirchhoff's laws and Ohm's law here to make some predictions. So in each of the following experimental setups that you're going to see, we are going to predict the total resistance based off of our knowledge of Kirchhoff's law. So the first setup is nice and simple. We've seen this one before. It's one 100 ohm resistor in series. Okay, so for this one, if we have one resistor with a 100 ohm resistance, typically we would predict that the resistance would be approximately 100 ohms. And if we were to plug this in, we would find that a measured value would again be roughly 100 ohms. Okay, nice and simple series circuit. In a series circuit, remember RT equals R1 plus R2 plus any other resistor up to infinity. Okay, set up the following configuration with two 100 ohm resistors. So if we have two 100 ohm resistors, as we saw in a series circuit, we might anticipate that the total resistance is 200 ohms. But some of you may have been looking ahead at Kirchhoff's laws, as we see in our formula sheet, and have noted that the total resistance in parallel is equal to 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 up to infinite number of resistors. So if that's the case, 1 over RT equals 1 over R1 plus 1 over R2, 1 over RT in this instance equals 1 over 100 ohms plus 1 over 100 ohms. Employing some basic algebra, we know that we want to invert these numbers because we're looking to solve for RT. So to do that, we can multiply both sides across, and we end up with RT equals 100 over 2. Okay, I may have skipped a step there, so just to summarize how I got from here to here. 1 over 100 plus 1 over 100 is equal to 2 over 100. Okay, is equal to 1 over RT. In order to get there, we need to multiply by RT, multiply by 100, and divide by 2. So what we end up with is RT equals 100 over 2. Simplifying that, our final answer, 50 ohms. And if we measured this using an ohm meter in lab, we would see that we reach a resistance of roughly 50 ohms. So employing the same theory, 1 over RT, if we had three 100 ohm resistors, 1 over 100 plus 1 over 100 plus 1 over 100 is equal to 3 over 100. We're looking to solve RT. We know that RT is going to be approximately 33.3 ohms. Okay, given three 100 ohm resistors in parallel. By now, we've certainly recognized a pattern. We're going to assume that 1 over RT is equal to 5 over 100. So RT in this instance is equal to 100 divided by 5, or approximately 25 ohms. Okay, we can use this to then predict the number of the total resistance given any number of total resistors. So certainly we could employ 5 resistors and get a total resistance of 20, or we could employ 6 and get a total resistance of 16.67 ohms. You would need to use your calculator for that one. So what happens to the size of resistance in a series circuit as resistors are added? Does resistance get larger, or does resistance get smaller? Well, we've seen from anecdotal evidence that resistance gets larger as we add more resistors in series. What happens to the total resistance in a parallel circuit? Resistance gets smaller. Let's think about this with respect to current. We know that V equals I times R. Or in this case, resistance equals V over I. As resistance goes up, current goes down. So in this case, as resistance goes up, current goes down. And in this case, as resistance goes down, current goes up. Now, what's the difference between a series circuit and a parallel circuit? Let's take another look at Kirchhoff's laws. For series circuits, delta I is I1, is I2, is I3. I've denoted this as delta I. You may have just seen it as IPS for the current at the power source. In a parallel circuit, IPS is equal to I1 plus I2 plus I3 all the way to an infinite number of wires. So the additive nature of the current here indicates that as we continue to split our electron flow, we are going to reduce the overall, we're going to change the overall flow rate. Okay, you can see that here in your formula sheet. Okay, the current going in is always equal to the current going out, is equal to the additive total of all of the currents for a parallel circuit. From this, we can deduce some form of analogy for you guys to conduct this to your memory, commit this to your memory. So the total resistance in parallel circuit can always be described in a mathematical equation as the total resistance inverse, the 1 over total resistance, is equal to the reciprocal of each of the additive resistances. So I want you to go back and show that this equation is correct in your notes and submit your notes to Edsby.